Okay, our second problem is going to be a similar type situation that we had with our first problem, except for now we're going to be dealing with two turbines. Okay, so turbine 1 and turbine 2. Okay, now usually these turbines are connected on a single shaft, and what we're going to have is coming in here, state 1, going out, we're going to have something called a reheater. And I've done a problem similar to this in the in-person sessions. But now we are told this reheater, we're going to reheat it with air. Okay, so there's going to be air coming in here. It's going to be going this direction. And so let me label some states. 1, 2, 3, oops, that's not the state, and 4. And then we're going to have 5 and 6. And so what often happens with the turbine is we reheat. So this is a reheater in the middle of the two turbines. Okay, so let me give you some state information here. So state 1, we have H2O, and it's going to have a temperature 1 is equal to 600 degrees Celsius, and a pressure 1 equal to 20 bar. State 2, it's water. The temperature at 2 is going to be equal to 400 degrees Celsius, and the pressure at 2 is going to be equal to 10 bar. State 3. State 3, uh-oh, still water, but we only know we don't know the temperature at 3. We just know the pressure at 3 is equal to 10 bar. State 4. We now know that it's still water, and we know that the temperature at 4 is equal to 240 degrees Celsius, and we're down to pressure 4 is equal to 1 bar. Okay? And let's look at states 5 and 6, and I'll put it over here. Yeah, I can still work it in. State 5, this is going to be air. And they tell us a few things about the air. They tell us the mass flow rate at 5 is equal to 1,500 kilograms per minute. They tell us that the temperature at 5 is equal to 1,500 Kelvin. And they tell us the pressure at 5 is equal to 1.35 bar. And finally, state 6. They tell us that the temperature at 6 is equal to 1200 Kelvin, and the pressure at 6 is equal to 1 bar. Okay, so there's some pressure drop inside of that reheater, and with the air side, there's no pressure drop on the water side. But we're taking some heat from the air and putting it into the steam flow. Okay, so the questions that they ask here. So this is what they say. This is what the problem statement says. Separate streams of steam and air flow through the turbine and heat exchanger arrangement shown. Steady state operating data are applied. Okay, there we go. We can assume here steady state. Heat transfer with the surroundings can be neglected. Okay, this means that Q dot stray is equal to 0. As can all kinetic and potential energy effects. So this is kinetic energy and potential energy, approximately equal to 0. Determine the temperature 3. So what we're going to try to figure out is we're going to try to figure out what this is. This is what we want to find. Temperature 3, what is that? And the power output of the second turbine. So power output here, what is the power output here? What is W dot of T2? Now, we happen to be given what the work of the first turbine is. It's going to be equal to the power of the first turbine is 10 megawatts, or 10,000 kilowatts is what we're given here. Okay? So, how do we find this information? Well, it's all kind of sticking around this control volume. We need to get around this control volume temperature 2, turbine 2. But with turbine 2, we don't know a state coming in, and we don't know what the power is. So we have to go backwards. We have to go backwards. Think about, okay, we can find mass flow rate. Well, if we use the reheater as our control volume, we can't figure out what the mass flow rate of the steam is, or the mass flow rate of the H2O is, and we don't know what state 3 is, so we have two unknowns. We have to go all the way back to this first turbine, and with this first turbine, we know what the power is producing, and we can set the state 1 and state 2. The only unknown in that situation is going to be the mass flow rate of the cooling water, the mass flow rate of the steam, so we can solve for that. So let's go back here, and let's say that our control volume is turbine 1, and we can write our equation, dE dt is equal to Q dot minus W dot plus the summation of my mass flow rates in times my enthalpy in plus my kinetic energy in plus my potential energy in minus the summation of my mass flow rates xting times my enthalpy xting, kinetic energy xting plus my potential energy xting. Now, you might be saying, Dr. Wyckoff, you said some of that stuff goes to 0. Can I just make it go to 0 when I'm writing out this equation? Of course you can. I'm doing it complete, but you might find it's just easier just to do that in your head, and that's fine. I want you to do that. But I also want to let you know that if you do skip a step or you miss something out, then I'm going to have to count you off on that. So if you show me your work, sometimes that might give you some reason or some places where I can give you some partial credit. Okay, so this goes to 0, 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 and we're left with this equation that the power for the turbine is going to be equal to the mass flow rate times H1 minus H2. Okay, or the mass flow rate of the H2O is going to be equal to W dot of the turbine all over H1 minus H2. Okay. Now, what did they give us? They gave us the power here was 10,000 kilowatts. And now we have to go through here at 20 bar and 600 degrees Celsius and 10 bar and 400 degrees Celsius and set our states. I am not going to go to my tables and I'm just going to say these are both steam. You need to verify that if you have questions. And I'm going to give you the values for what H1 and H2 are. So if you want to go look it up, you go look it up, pause here, come back with me, and we'll figure this out. Okay, so I found that this is going to equal 3,690.1 minus 3,263.9 kilojoules per kilogram. Okay, what is a kilojoule? A kilowatt? A kilowatt is a kilojoule per second. We're good to go there. We're going to get units of kilograms per second, which is mass flow rate. And the mass flow rate we're going to find is 23.46 kilograms per second. Now we know what the mass flow rate is. We're well on our way to figuring out how much power the turbine has. We've gotten rid of one of our unknowns. Remember, there were 3 unknowns in that second turbine. There was the mass flow rate, there was the state coming in, state 3, and there was also how much power we're producing, and that's what we're trying to find. So now what we have to do is go to our second control volume, which is going to be the heat exchanger, and analyze that heat exchanger to find out some information about state 3. So now we're going to say the control volume is our heat exchanger. Okay, control volume is a heat exchanger. What is that going to show us? So we're going to say that the change in energy of the control volume with respect to time is equal to Q dot minus W dot plus the summation of my mass flow rates in times my enthalpy in, kinetic energy in, plus my potential energy in, minus the summation of my mass flow rate xting times my enthalpy xting, kinetic energy xting, plus my potential energy xting. Okay, and so steady state, heat exchanger is going to have no straight heat transfer. Heat exchanger has no power and no kinetic or potential energy effects. And we're going to get ourselves down to this. 0 is equal to the mass flow rate at 2 times the enthalpy of 2 plus the mass rate of 5 times the enthalpy of 5 minus the mass rate of 3 times the enthalpy of 3 minus the mass rate of 6 times the enthalpy of 6. Okay, this is what's coming in, and this is what's going out of that control volume. And we know, just like we did before, that the mass rate of 2 is equal to the mass rate of 3, which is equal to the mass flow rate of our H2O. And we know that the mass rate of 4 is equal to, mass rate of 5 is equal to the mass rate of 6, which is given to us as 1,500 kilograms per minute in the problem statement. And so I'm going to rewrite this as this. 0 is equal to the mass rate of the water times H2 minus H3 plus 1,500 kilograms per minute times H5 minus H6. Okay? Now, I know this. I just calculated the mass rate of my H2O. I know this. I can set that state, that H2 is the same H2 as I had in my first step, in my first control volume. H5 and H6, it's air, and I gave you the temperature. The problem statement gave you the temperature for this, so this and this can be easily found. The only unknown we have is H3, so we can solve for H3. So how are we going to do that? Well, it's going to look something like this. Let's do this. So mass rate of the water times H3 minus H2 is going to equal 1,500 kilograms per minute all over, I'm going ahead of myself, times H5 minus H6. Now I'm going to get this over here, and I'm going to say that H3 is going to be equal to H2 plus 1,500 kilograms per minute divided by the mass rate of my water times H5 minus H6. Okay, so in this we know H2, like I said. H2 is given to us as 3263.9 kilojoules per kilogram plus, well, our mass flow rate is given to us in kilograms per minute, and our mass rate of water that we just solved was in kilograms per second. So let's make sure this is all on the same basis here. So 1,500 kilograms per minute. And I'm going to say here that in 1 minute, there's 60 seconds. And now I can use the 23.46 kilograms per second. Those units are going to cancel. And then we have H5 and H6, and we look those up in table A22. Table A22 gives us for H5 1635.97 minus 1277.79 kilojoules per kilogram. Okay, so all our units here are going to cancel out. All going to cancel out, and we're going to get kilojoules per kilogram plus kilojoules per kilogram. And we can add all of that together, and we're going to get this number. We're going to get this 3645.6. Okay, now, what do we know? This is H3. Okay, H3 is this value. We also know that our pressure at 3 is equal to 10 bar. Okay, we want to know what the temperature is at 3. That's what one of the problem statements said. So we're going to go to our document camera. We're going to go look at 10 bar. First of all, so that's table A3. We're going to go first look at saturation, and we're going to go to look at 10 bar, 10 bar, 10 bar, and we're going to look. And this is what we're going to start with. Here is our saturated liquid enthalpy, and here's our saturated vapor enthalpy. We're well above that, so that means we're still a gas. So we're going to go to our 10 bar gas tables. 10 bar gas tables, and we don't know what temperature is, so we're going to go look at our enthalpies, which is our third column, and we're going to look for 33,645. It's going to be between 540 and 600. So we're going to have to interpolate. Okay, we're going to have to interpolate. So, interpolation, one of our favorite things to do. One of our favorite things to do. So, we are going to say this is between 540 and 600. Okay, and I did the interpolation for you. I'm going to do it. I mean, if you want to practice interpolation, do it now, and I'll show you the number here. I want to make sure. I want to, not keep you too long here today because we're just doing some problems. But I think you're pretty comfortable with interpolation by now. This is going to give me 576 degrees Celsius. That's what my T3 value is. Okay, my T3 value. So now what it ends up being is I now have to do my third control volume, because now that I know the enthalpy coming in at 3 and I know the mass flow rate of the steam, all my only unknown that I have is going to be my power. Now, the control volume, my control volume is turbine 2, and turbine 2 is going to be just like turbine 1. So I don't really have to rewrite my energy equation. I can just say that W dot is going to be equal to M dot times Hn minus H exiting. And here, we're going to say that W dot is equal to the mass rate of my H2O times my Hn, which is H3, minus my H exiting, H4. And we know, we just found H3. We just found H3 up here. H4, we're going to look up at 240 degrees Celsius, 1 bar, which is in table A4. Okay, 240 degrees Celsius, 1 bar, so let's look it up. One bar, 240 degrees Celsius is going to give me 54.5 kilojoules per kilogram. And we just found M dot in the earlier part of our problem. So now we can solve for our power, which is going to be something in the megawatts actually, but we're going to put in kilowatts. I'm going to give you a 5-digit answer, and that will get you out of today. And we've spent about 40 minutes here working on problems, and that's where I'm going to end it. I'm going to end it there a little early so that we can get some time to work on some homework or get out of the day or just go to bed, because that's probably what's happening for you. We just want to get this lecture done and go to bed. So do this quick calculation and be done with it. This is the last material for exam 2. We'll be releasing some practice exams and some things that you can work on for this exam. If you have any questions, please let me know. And other than that, we'll see you on Wednesday.